For more than a century, the development of the internal combustion engine was dictated by a small group of established industrial powers. Germany designed the modern blueprint, while Japan spent decades refining the mechanical tolerances. From Mercedes to Toyota, these manufacturers optimized every valve and piston to define the limits of the machine. Eventually, the consensus across these global giants converged on a single shared reality. Geely announced they had successfully verified a new engine reaching 48.41% thermal efficiency. The figure shocked the industry. For legacy engineers, moving past 41% was considered a commercial impossibility. To back up the claim, Geely displayed a high-volume assembly line, signaling their intent to move this technology from the laboratory to the global market. This single metric suggests that the technical lead once held by Germany and Japan is no longer a certainty. China is now competing at the very edge of what the industry believed was physically possible. Toyota's work in Japan had long defined the industry's technical benchmark. The release of their dynamic force engine, which hit the 41% mark, was hailed as a monumental feat of engineering. Reaching that number required years of research focused on microscopic mechanical friction and air-fuel mixtures. Every 0.1% gain cost millions, but this success led to a quiet stagnation. Automakers convinced themselves that since they had hit a thermodynamic wall, there was no reason to keep investing in combustion. The West accepted 41% as the finish line, creating a gap in innovation that no one expected would be filled. Legacy manufacturers in Europe and America responded by committing to a future that was exclusively electric. This pivot overlooked immediate hurdles, like grid capacity, lithium scarcity, and the weight of massive batteries that limit range and increase costs. While the West bet everything on a total electric transition, China maintained a dual-track strategy, funding a new generation of high-efficiency hybrids. These vehicles allow for high-speed travel across massive urban infrastructures where charging networks are still catching up. By moving away from internal combustion prematurely, the legacy manufacturers left a technological vacuum. China spent that time perfecting the very technology the West abandoned. To understand how Geely pushed past the industry limit, we have to look at how much energy a standard engine actually loses. This shows the math of a typical gasoline engine. 30% of energy is lost through exhaust, 30% is absorbed as heat, and 10% by internal friction. Ultimately, only 30% of the fuel's energy reaches the wheels, meaning 70% of every gallon is wasted. Because the machine is so inefficient by design, finding even a few percentage points of improvement requires overcoming massive thermal barriers. The primary barrier is the Carnot limit, a law of physics stating that to get more work out of an engine, you must produce a hotter explosion. But increasing that heat creates a dangerous trade-off. Push the temperature too high, and the engine begins to destroy itself. Under extreme thermal stress, the fuel ignites prematurely. This causes engine knock that can warp the metal and shatter the pistons in seconds. The risk of this mechanical failure is precisely why Toyota and other manufacturers stopped their pursuit at the 41% mark, which leaves a massive technical question. If 48.41% requires heat levels that should melt a commercial engine, how did Geely achieve it? In the early 2020s, the automotive world decided the future was settled. The internal combustion engine was declared a relic, and the industry raced toward a singular all-electric vision. From Tokyo to Stuttgart, and through the assembly lines of Detroit, the consensus was absolute. Batteries would replace gasoline, and automakers invested hundreds of billions to retool their entire production logic. But that vision carries a literal weight. A modern electric SUV requires a massive energy source, relying on complex battery packs that can easily exceed half a ton. That heavy weight demands massive high-voltage charging networks. Yet across South America, Africa, Southeast Asia, and even vast rural stretches of the West, that basic infrastructure simply does not exist. Chinese engineers looked at the physical realities of the market and identified an entirely different business logic. They calculated that the world will require a bridge between gasoline and electricity for decades, and mastering the engineering for that phase represents the largest market opportunity in the industry. While Western governments legislated the death of the gasoline engine, China's largest automakers started redesigning it from the ground up. BYD launched the first strike, For 20 years, standard hybrids operated on a compromise, forcing the gasoline engine and the electric motor to constantly trade off the work of physically turning the wheels. This chart maps the core flaw. As a driver accelerates or brakes, the engine's RPM fluctuates, constantly falling out of its optimal efficiency zone. BYD solved this by decoupling the gas engine. It acts strictly as an onboard generator, locking into one optimal RPM indefinitely. Operating in that perfect band yields a thermal efficiency of 46.06. In an industry where a single percentage point of improvement can take a decade of research, BYD closed a massive efficiency gap in a fraction of that time, forcing a sudden recalculation from its global competitors. BYD was only the opening move. Almost immediately, Geely began pushing toward a 48% efficiency threshold. Reaching that number required moving past standard mechanical tweaks. Geely had to look at the physics of how fuel actually burns. This diagram shows a traditional combustion stroke. Gasoline and air mix poorly, meaning when the spark plug fires, the flame front spreads slowly. While that flame travels, its heat dissipates into the metal walls, wasting potential kinetic energy. To stop that leak, Geely altered the airflow geometry entirely. Their high-tumble induction system whips the intake air into a violent, vertically spinning vortex right before the spark. By igniting a concentrated fire tornado, the combustion happens almost instantaneously across the entire chamber. The fuel burns faster and more evenly, channeling maximum physical force directly down into the piston before the heat has time to escape. Generating that much concentrated force creates another hurdle. You have to run a very high compression ratio, squeezing the air and fuel tightly together. But under extreme pressure, standard engines tend to destroy themselves. The ambient heat and immense pressure cause the fuel to detonate before the spark plug even fires. This premature explosion, known as engine knock, sends a destructive shockwave that can crack a piston in minutes. This thermodynamic map details Geely's solution, an engine block engineered to maintain two distinct, conflicting temperature zones at the same time. The upper cylinder head is aggressively cooled to prevent premature ignition caused by heat. Meanwhile, the lower half of the engine block is kept intentionally hot. This thins out the motor oil, reducing the mechanical friction as the piston moves. Maintaining a freezing top half and a boiling bottom half allows the system to run extreme compression metrics that would normally tear the metal apart. Creating highly efficient power is useless if you lose it on the way to the wheels. This schematic outlines a standard transmission. It uses an intricate maze of clutch packs, hydraulic lines, and heavy gear sets to manage torque. Every single piece of moving metal creates friction, absorbing kinetic energy and bleeding efficiency. Geely bypassed this friction by removing the mechanical gearbox entirely. They replaced it with an electromechanical system that routes power using direct electrical connections rather than interlocking physical gears. Stripping out the physical transmission hardware converts the vehicle from a mechanical assembly of moving parts into an integrated energy management system. Keeping the engine in dual thermodynamic states while balancing the electrical routing and the generator's RPM requires micro-adjustments that human reflexes cannot manage. To control the hardware, Geely installed a dedicated artificial intelligence processor right at the center of the powertrain. This chip evaluates the car's energy needs 50 times a second. It continuously pulls in external data, reading the immediate traffic flow, the slope of the upcoming road, and the exact physical topography of the route ahead. Using that environmental data, the AI calculates the most efficient method of propulsion in real time. It decides exactly when to pull from the battery, when to ignite the generator, or when to link the drive motor straight to the wheels. At this level of integration, the machine acts as a mobile power plant, predicting and managing its own internal grid as it moves. Western automakers staked their survival on a complete shift to pure electric vehicles, waiting for the rest of the world to build the infrastructure to support them. But by radically redesigning the combustion engine, China built a highly efficient, practical bridge, and the engineering that controls the transition will determine who ultimately dictates the future of the global market. For the last decade, major automakers and international regulators aligned on a single, uncompromising path forward: pure electric vehicles. To achieve the driving ranges consumers demand, Electric cars require massive, heavy battery packs. Those batteries rely on a vast industrial footprint, evaporation ponds, complex mineral extraction, and highly localized supply chains. For the driver, this translates into physical bottlenecks, finding an available, working station and waiting out the battery gauge during holiday travel. The industry accepted this compromise. Range anxiety and charging delays were viewed as the necessary tax for eliminating gasoline. Then, a Chinese automaker introduced a vehicle that ignores that compromise entirely. Geely recently unveiled a large family-sized hybrid SUV. This map tracks a single tank of fuel. The vehicle consumes under 3 liters per 100 kilometers. That efficiency allows it to travel over 2,000 kilometers without stopping. That covers the distance from Berlin to Madrid, or New York to Miami. It offers the silent cabin and instant torque of a standard EV. But when the energy runs out, the driver pulls into an existing gas station and refuels in 3 minutes. By offering EV performance without the infrastructure dependency, this vehicle removes the friction of the transition. It gives buyers the exact convenience they were told they had to sacrifice. To understand how fast this happened, look at the technology itself. The internal combustion engine is a distinctly European invention. American manufacturers commercialized it. They built the assembly lines that pushed engines to a mass scale. Then, Japanese engineers spent decades refining the mechanics. They carved out efficiency improvements by fractions of a percent, eventually dominating early hybrid technology. That was the benchmark. Chinese automakers have now overtaken those legacy efficiency metrics, while simultaneously scaling up their own battery production. The result is a physical volume of vehicles flooding out of domestic ports and into the global supply chain. By moving into frontier engineering, China is now advancing the specific internal combustion technologies that once anchored European and American power. The opening for this shift was created by a specific policy choice. Western governments and legacy automakers committed to a completely electric future, mandating a hard transition away from gasoline. That mandate relied on a technical assumption. Regulators and CEOs concluded that after 150 years, the internal combustion engine had reached its absolute physical limit. Chinese companies operated under a different assumption. While they aggressively cornered the global EV market, they also poured engineering capital back into the internal combustion engine. Geely engineers simulated extreme thermal dynamics inside the combustion chamber, achieving a highly controlled fuel vortex. They pushed the combustion process to efficiency levels previously dismissed as impossible. The boundary of the engine wasn't dictated by the laws of physics. The boundary was the consensus that the technology couldn't be improved. By halting major internal combustion research to focus purely on electric cars, Western automakers abandoned their strongest technological advantage, leaving a massive gap in the market. The new metric defining the survival of these companies is thermal efficiency. This chart plots the exact progression. Standard legacy engines plateau around 41%. Geely pushed to 46.06%, and their latest reached 48.41%. At the 50% threshold, the cost per kilometer drops so low that Western engines completely lose their primary competitive advantage, affordability. This compounds an existing problem. Chinese firms already process lithium, manufacture the battery cells, and produce the most affordable EVs. Now, by solving the hybrid equation, they have removed the last structural defense of legacy automakers. They control the transition from both ends. For generations, the rules of the road were dictated by a handful of cities: Detroit, Stuttgart, and Tokyo. Today, those hubs are being rapidly outpaced by highly integrated tech zones built directly alongside megafactories. The center of gravity for automotive engineering has effectively shifted east. This massive concentration of modern industrial capacity, spanning all the way from raw battery chemistry to fully automated global logistics, realigns the global hierarchy of manufacturing. The future of transportation is no longer a Western project. The next chapter is being written right now in cities like Hangzhou.